Hi everyone, my talk today will be about aspects of the renormalization group and more specifically the Epsilon expansion and how we find fixed points which describe conformal field theories in the Epsilon expansion. To set a proper context, I thought I should give a short video introduction to this general and very exciting research area. And I should start by saying that the Epsilon expansion and this general research area is of course a 50-year-old research area that still is producing new and exciting results. So I hope some of you will be interested to participate and come talk to me about, for example, the open questions I will mention at the end of my talk. So let's get started with the context, and perhaps the best way to start is to discuss the fine structure constant, which we're all familiar with, usually denoted by the Greek letter alpha, and given the approximate value 1 over 137. Now, this is the value that we get when we perform experiments in everyday energies. However, in fact, this is not a fixed value for this quantity. This quantity is a function of the energy scale, denoted by mu, at which we perform the experiments. So we have to go back and put constant in quotes here. It's not really a constant, it's a function of the energy scale. And the way it changes with the energy scale is captured by an RG equation. Now, suppose you were to perform an experiment where the energy is the same as the mass of the Z boson, then what you would find is that it's not 1 over 137 anymore, but it's rather about 1 over 128. It's an increased value, therefore, compared to lower energies, and as I already said, this dependence on the scale mu is described by an RG equation. The RG equation tells us that it is a non-trivial derivative of this quantity with respect to the energy scale mu. This is of course equal to this, and this is something we refer to as the beta function for, in this case, alpha. Now in QED, we had, if the mu is positive, which means we're going to higher energies, the alpha is also positive, as you see by comparing these two numbers, and therefore the beta function of QED is positive. And in fact, at one loop, a short calculation will show that the beta function goes like alpha squared. If you were to plot this, you would have a very simple behavior, valid when alpha remains small. Very good, so that perturbation theory makes sense. Very good. So this is the case of QED, and there are other examples of theories where the beta function may be negative, like for example the case of QCD, where we have a property called asymptotic freedom, which makes QCD more weakly coupled at high energies than at low energies. So this is asymptotic freedom. What we are interested in are cases where the beta function changes sign, and when it changes sign, it passes through zero, and we're interested exactly in those zeros. So let's see an example of that. You can write down perhaps a theory that displays this, perhaps the most famous example discussed in this context is a theory with the canonical kinetic term, and we have an interaction which is a quartic interaction. This is a scalar field phi, and we have a quartic interaction. So this theory is a theory with a Z2 symmetry, where if phi goes to minus phi, the theory remains invariant. And the beta function in this theory for the coupling lambda can be computed, and for some properly rescaled value of this coupling lambda, it is 3 lambda squared. This is if you perform the calculation in 4 dimensions. And this is the one-loop calculation. In perturbation theory, you would here obtain some further corrections at order lambda cubed. Now, this does not allow us to do perturbation theory, but Wilson and Fisher, a long time ago, realized that perhaps we can make a parameter up here with which to perform perturbation theory. And that parameter arises when we consider the space-time dimension d not to be 4 anymore, but perhaps we'll take it to be 4 minus epsilon. The motivation here is to go to 3 dimensions. So eventually we want to take this epsilon to 1 because 3-dimensional conformal field theories describe classical critical phenomena which are non-zero temperature phase transitions. When you go to 4 minus epsilon dimensions instead of 4 dimensions, the beta function picks up an extra piece. And now it's minus epsilon lambda plus 3 lambda squared. And so, obviously, if I were to plot this, we would have a more interesting situation where we start off negative at small lambda, and eventually the lambda squared term will win, and we will turn positive. There are 2 fixed points here. We have the trivial fixed point where we don't have any lambda. This is obviously a 0 of the beta function. And we have a non-trivial fixed point over here. This is the fixed point lambda equals 0. This is the fixed point lambda, it's epsilon over 3. This is what we refer to as the Ising model, when epsilon goes to 1. Now, of course, epsilon going to 1 is not a well-defined limit to take. So when we perform computations, we will have to properly set epsilon to 1 through some resummation or perhaps some proper estimations of these results that we will calculate. I will not get into the details of that, but this is something that tells us that there is a way to find 3-dimensional theories by continuing in the space-time dimension away from 4 dimensions and into 4 minus epsilon dimensions, and then taking the epsilon to 1 limit in the end to capture 3-dimensional conformal field theories. This is a strategy that works more generally. You can do it in 6 minus epsilon dimensions, you can do it in 3 minus epsilon dimensions, you can do it in many different contexts. Scalar theories, you can add fermions, you can have supersymmetry. There are many, many different contexts in which these equations, such equations, can be analyzed. And what happens here is that we have what happens here is that we have a theory, the free theory, in the ultraviolet, and then we perturb by the phi to the 4th operator over here, and we obtain an RG flow, this parameter mu, into the IR, into another CFT, which is the Ising theory. The non-trivial conformal field theory is obtained in the infrared. And this is a very important example because there are many systems that are described by the Ising model. One of them is the Curie point of a ferromagnet. Another one is the critical point of water. So at the critical point of water, you have a theory, specifically at the critical point of water, you have a theory that is described by exactly the same observables as the theory describing the Curie point of a ferromagnet. So here you see 2 very different systems, a ferromagnet and a liquid, being described by the same physics, which points to the fact that the conformal field theories are universal, have a certain universality, and therefore their study is very important. Perhaps the best way to say it is that at the fixed point, the theory is interacting, but perhaps only the most essential effects of those interactions are apparent, and therefore the universal behavior emerges. So this is perhaps the most well-known example of conformal field theories, conformal field theory in 3 dimensions. And in my presentation today, I will be discussing generalizations of this. So it was a very simple case here where we had a simple quadratic equation to set to 0. So we obviously found 2 fixed points. But what happens when we have many fields, phi I, where this I can go from 1 to some number n, and we write down something like the Ising model. So what we're going to do is we're going to write down a theory which involves all these different fields. Again, we have a kinetic term, but now it's not just lambda phi to the 4th, but we have something that looks like this. For a symmetric tensor lambda ijkl. A one-loop computation in this theory gives us a beta function for lambda, which now is a symmetric tensor. Starts like minus epsilon lambda ijkl plus lambda plus 2 more terms here needed to make this this over here into a symmetric function in the indices ij kl. So obviously we're going to have many beta functions now depending on the n we choose, because this is a symmetric tensor. The number of lambdas is 1 over 24 n times n plus 1 times n plus 2 times n plus 3. So it scales like n to the 4th, and therefore we have at larger n a proliferation of beta functions and couplings, and these beta functions are coupled quadratic equations involving all these different couplings, and it's going to be very hard to find fixed points. If you have 2 or 3 or 4 of them, it's not that hard, but the moment you have, I don't know, 100 of them, it's going to be virtually impossible to analytically find fixed points. So the strategy that has been used in the literature for many years was to impose a symmetry that relates all these beta functions and effectively then reduces the number of couplings and beta functions you have to deal with. However, the strategy we will be employing is to come up with a numerical method to analyze these equations. It will be an optimization method, I will explain during the talk. And with this method, we were able to find literally hundreds of new fixed points. This is something very exciting, and in the end what we want to do is, within the epsilon expansion, this very well studied method, what we want to do, our dream if you want, would be to classify fixed points within this paradigm. We want to know all possible fixed points that can be obtained within the epsilon expansion. Our motivation is, of course, their applications to critical phenomena, but we want to work more generally. We don't care here about the applications, but what we do care about is what possible fixed points can even arise in this context. So this will be what I will be talking about, and as I said in the beginning, I will be offering an overview of my recent work on this, as well as a large variety of open questions that I would be happy to discuss with any of you.